Now, let's look at a question. We're given now a haloalkane. Now, already I told you that when you see alcohols, alkanes, haloalkanes, and alcohols, you think about these two reactions, please, substitution or elimination. So you can see that, okay, we're having a haloalkane, depending on the conditions. Remember the condition I said CEDS, CEDS. So you know that concentrated, elimination. Dilute, substitution. So already you see that, this is dilute sodium hydroxide. Definitely, this must be dilute, must be substitution. This one is concentrated sodium hydroxide. This must be elimination. So already you know reaction 1 and reaction 2. Reaction 1, because it's dilute, is substitution. Reaction 2, because it's concentrated, is elimination. You see, if you have knowledge of all the reaction conditions, I'm telling you, it will be very easy for you to spot these reactions and to be able to answer the questions. And then you're able to see that that reaction is able to form. We had a haloalkane forming an alcohol. Definitely, during substitution, when we form from haloalkanes to alcohols, we're calling that a substitution, and the type of reaction is called hydrolysis. Remember, we can use dilute sodium hydroxide, or we can use water. It's not only that, it's water and mild heat, because they're going to ask you about the other reaction conditions. So you know, for substitution, we don't want that, we just want mild heat. And then we're saying for hydrolysis, it's either we'll use water or dilute sodium hydroxide. When you're using the concentrated sodium hydroxide, definitely you are going to undergo elimination. Remember, elimination, we are forming unsaturated, meaning that we'll have our double bonds here. So double bonds, compound Q will be unsaturated, definitely. And for unsaturated, you know, USA is only one reaction that unsaturated undergo. So when you see an unsaturated, definitely it must form a saturated, and the reaction is called addition. So you know reaction 3 is addition. Why? Because we are having unsaturated. So we're saying when you see an alkene, definitely you know the reaction that an alkene will undergo is addition reaction. So remember, you have that told you about substitution and elimination. Now we are bringing you alkenes to say when you see alkenes, you know they are unsaturated. Definitely USA, they are going to be saturated, and the reaction is called addition. And you must know the types of reactions, the types of addition, the types of elimination, the types of substitution. Now name the type of reaction represented by 1. Already we talked about that. We said it's substitution, and then that is the type of reaction. And then we'll accept hydrolysis because we are being specific. And then is the methyl butan or 1-ol, is this a primary, secondary, or tertiary alcohol? So you're able to see that it's on the terminal carbon. Definitely that must be primary, because we have seen with propan 1-ol, propan 2-ol. Propan 2-ol was secondary, propan 1-ol was primary. So at least it gives you so that you're able to see that this is a primary alcohol, and the reason you are saying the carbon atom bonded to the OH is bonded to one other carbon, or the OH bonded to the carbon atom, which is bonded to 2 hydrogen atoms. So you can talk about the hydrogen atoms or the carbon atoms. Will accept any of those. So you are fine. Write down the structural formula of compound P. And then you see P is C5H11Br. Now, don't make a mistake of thinking that this structure C5H11Br has no branch. Always look there. It's saying 2-methyl butan. So you can see that in carbon number 2, we have a methyl. There's a branch there. There's a side chain there. There's a substituent in carbon number 2. So don't make a mistake when you have to draw this structure. Definitely the longest carbon chain must have 4 carbons. And then that's what we are having. In carbon number 2, we must have a methyl, you'll get 1 mark for that. In carbon number 1, we have a bromo, you'll get 1 mark for that. In the longest carbon, the whole structure is correct, another mark. Just look at the number of marks, 3 marks if we are doing that correctly. So take drawing of our structural formulas, very important. Name the type of reaction represented by 2. So you are able to see that 2, definitely we said elimination. So you can see that we're going to eliminate because we're using concentrated, and then you can call it elimination. We'll accept if you are specific to tell us the type of elimination, which is dehydrohalogenation or dehydrobromination. Now, to which homologous series does compound Q belong? And then, obviously, because of elimination, you know it must be alkenes. Now, these are alkenes or alkene, it's fine. And then you are able to answer that. And then name the type of reaction represented by 3. So already you have seen we have unsaturated forming saturated. That must be addition. Always when you see unsaturated or alkenes, you know they undergo addition reaction. Write down the IUPAC name of compound R. You are just putting the Br there, so you know that you will have 2-bromo, 2-methyl, 2-bromo, 2-methyl. Remember, you're bringing the bromo there. 2-bromo, 2-methyl butane. Here we're talking to the issue of your product now, to say that your product must be in terms of the rules, to say no. Remember, your bromo will go for the carbon, that the poorest carbon. The poor here becomes much poorer. So you must be able to know that the bromo will go to carbon number 2 because it has less number of hydrogens. And then we are saying always remember cracking as the chemical process in which longer chain hydrocarbons and molecules are broken down to shorter, more useful molecules. And we are saying focus as well on thermal cracking and catalytic cracking. And we are saying the products of cracking is either an alkene and alkene or alkene and hydrogen. So cracking, we can crack at any point. You can see we can crack and remove CH from butane, can remove CH2 and propene there. And then that is the structure. We can crack in the middle and form ethane and ethene. So that is what we are talking about in terms of cracking, and be able to differentiate between thermal, where we're using high temperature and high pressure, and catalytic, where we're using catalyst for the reaction to take place. Now, example of combustion or oxidation reaction, and then the example there we have butane, which is a fuel in our big lighters. I think you have seen the lighters. And then we are saying here it is alkanes plus oxygen to form carbon dioxide and water. The main thing, plus energy. The main thing we're saying, you will get a mark for the reactants, product, and everything is correct. When everything is correct, you will get your 3 marks. So please make sure you do all this and you understand even how to balance. In the event the balancing is not correct, definitely you will lose that 1 mark for balancing, but you'll get 2/3. Now, if we are to focus on question 8 and 9, because we said these are the questions that learners didn't perform well in the past. So you have done electrochemistry, still in your mind. Definitions. Don't forget, we said loss of electron is oxidation, and then it goes with the reducing agent, which is oxidized. So always you are remembering that your reducing agent is a substance. It's a substance that undergoes oxidation, or the substance that loses electrons, and it is oxidized. And then you know reduction is gaining of electrons, which is reduction, and it goes with the oxidizing agent, which is reduced. So you are able to always remember that the oxidizing agent is a substance. It's a substance that undergoes reduction, or a substance that gains electrons. And we are saying, don't forget, you have the anode and the cathode. You must know their definitions. Remember, we said this is the electrode where oxidation occurs or take place. Oxidation occurs at the anode. Cathode is the electrode where. Now, it's not a mistake that we are saying electrode where. So we are not necessarily saying the cathode undergoes reduction. We are saying it's the electrode where reduction occurs. So we are simply saying where the cathode is, they will be gaining of electrons. But electrons are usually gained by the cations, like when you have copper 2+. It's not copper that will gain electrons, it's copper 2+. And then it's very much important that you say it is the electrode where oxidation occurs. We call it a cathode. Hence, we are saying an ox and red cat, so that you are always reminding yourself the reducing agent and oxidizing agent. We talked to that. The issue of oxidation numbers. Please, you can answer these questions based on oxidation numbers. And then electrolysis. Remember, this is a process now. It's a chemical process now that converts electrical energy to chemical energy. Please differentiate between electrolysis and electrolytic cell. Please, we are strict when marking this. When you are defining electrolysis, you'll say it's a chemical process, then you talk about energy conversion. But when you are defining electrolytic cell, you will say now this is a cell that converts. You always start from electrical energy to chemical energy. When you talk about electrolysis, it's a chemical process that converts electrical energy. Energy conversion is the same, but the difference is that electrolysis is a chemical process and electrolytic cell is a cell. But both of them, they convert electrical to chemical energy. So always remind yourself of that. Now, I refer to this one as your solution, as the memorandum, the marking guideline. When you are having this one, when you have the understanding of table 4A and 4B, you are well armed for this type of reaction. Remember, this table we are saying is a table of standard reduction potential, which usually will say this is the ability to gain electrons. Remember, reduction is gaining of electrons. So this table shows the ability to gain electrons under standard conditions. And we are simply saying, what are the standard conditions that we are having? Our standard condition is the initial concentration. Not by mistake that initial must be there. It's initial concentration of 1 mole per cubic decimeter. That is the first standard condition. And then the second standard condition is that the temperature must be 25 degrees Celsius or 298 kelvins. If you prefer to use kelvins, it's fine. Temperature is equal to 25 degrees Celsius and pressure is 101.3 kilopascals. Please, if you go to table 4A on the data sheets there, you will see that temperature is given as 273 kelvins. So you have to add the 25 there to get the 298 kelvins when you talk about standard conditions. It means these values are valid under these conditions. But remember, pressure, it applies when you have gases. That's why I would always write pressure as number 3, because if you have no gases, no pressure, that will be a factor. The factors will be initial concentration of 1 mole per cubic decimeter and temperature of 25 degrees Celsius. And then we are saying now, this table is the ability, which means when I look, let me just look at the two. We're having the first cell, half cell, and the second one, Mg2 plus, and aluminium 3 plus there. If you look there, you can see now that we are having this situation. And if you were to look here on the right, there is an arrow. I hope you are having a hard copy of your table 4A and 4B, because you can't go to the exam without it. In the exam paper, you will definitely get a copy of table 4A and 4B. Don't bring it. It is part of your question paper. And then we are saying this is the table that you need when you are dealing with question 8 and question 9. And we are saying, if you look, there will be arrow that is facing upward there. It's saying increasing reducing ability. So we are saying that our reducing agent, when you look for the reducing agent, look up on the right, reducing agent. So look up on the right, and up on the right, I find the strongest reducing agent as magnesium compared to aluminium. So whatever is at the top there in terms of table 4B is our strongest reducing agent. So I know magnesium is the strongest reducing agent compared to aluminium. So we're saying aluminium and magnesium, they are both reducing agent. But in terms of strength, magnesium is a stronger, because the arrow there is facing upward. It's showing you the stronger reducing agent, because on the right of the table we have reducing agent, whereas on the left we have the arrow of table 4B. We have the arrow that is facing downwards. It's showing you where to find the strongest oxidizing agent. So oxidizing agents are on the left of the table. On the right, we have reducing agent. I want us to move like that. And then I was to ask you a simple question to say, if you are having a company, will you want strongest employees or weakest? Definitely, if you want to have good production, you'll want the strongest oxidizing agent and strongest reducing agent in order to have a spontaneous process. Remember, galvanic cell, we are saying this is spontaneous process. So definitely for galvanic cell, our reactions will always be between the strongest reducing agent on the right, which is magnesium in this case, strongest oxidizing agent on the left, which is bottom left there, you are having copper 2+. So definitely, I mean, you are having aluminium 3+, if I was to compare these two neighbors so that we don't waste time. So you're having your magnesium and aluminium 3+ there. And then those must be stronger reducing agent, stronger oxidizing agent. So these two, they definitely form the weaker ones. So which means magnesium is a stronger one, it becomes a reactant, which means magnesium must reverse to form magnesium 2+. Aluminium 3+ is a strong oxidizing agent, which means it must gain the electrons. Remember we said it has a bigger ability. Aluminium has a bigger ability. This number is bigger than that of negative 2,36. So aluminium 3+ has a bigger ability to gain electrons. Definitely it's a stronger oxidizing agent. So aluminium 3+ is gaining electrons to form aluminium. So our product are the weaker ones. The stronger ones on the left, the weaker ones on the right. And you can see by so doing, already we have written the overall cell reaction just by looking for the stronger reducing agent and a stronger oxidizing agent. And for question 8, that's how we are moving. And then with that, we are able to see, even if we say write down oxidation and friction, you can see that magnesium as a stronger reducing agent, definitely is magnesium is forming magnesium 2+, which means it's losing 2 electrons. We are reversing it. And for aluminium, as a stronger oxidizing agent, is aluminium 3+ plus 3 electrons forming aluminium, which means you write aluminium the way it appears there. It goes forward like that. And we are writing only one arrows, not double arrows. We're not writing the half reactions. And then if you combine these two, you are able now to say, okay, let's combine. But when we combine them, we're saying ionic. The ions must be balanced as well. So you can see that this has 2 electrons, magnesium. Aluminium has 3 electrons. So the first thing that you have to do is to definitely balance the electrons. So, okay, this one with 2, I'll multiply by 3. The one with 3, I'll multiply by 2. So definitely we'll say times 2. You multiply the entire expression. If you're multiplying this by 3, it will say times 3, times 3, times 3. And then for the aluminium part, you're multiplying by 2. You want to balance the electrons. Times 2, times 2. So you can see that when you multiply 2 electrons of magnesium by 3, you get 6. So this will be 6, this will be 6. They will cancel one another. And then you are able to write now the overall or the net cell reaction as 3 Mg, balanced one. 3 Mg plus 2 Al3 plus forming 3 Mg2 plus 2 Al. And then that is your 3 marks there. That is your 3 marks. And then after that, we will say, write down the cell notation. Look at this. Immediately from your overall, you can see that the anode, remember you said, we talked the issue of the stronger reducing agent, which is in your anode there. So you can see that we have the anode at the top and the cathode at the bottom. So definitely at the anode we have magnesium, at the cathode we have aluminium. So you are able to see that the reaction that is taking place at the anode, which is the loss of electron, A at the top, C at the bottom. So definitely this table, if you have it, you have all the skills. You are able to say, okay, when I write cell notation, I say A, B, C. When you're writing the half fractions, you said A and C. So you see it's A and C, you start with anode, then cathode. But when write the cell notation, you are saying A, B, C. You are starting with your anode now, which is your magnesium, or your 3 Mg forming your magnesium. It's magnesium forming magnesium 2+ plus 2 electrons. Then when you write this, you'll say Mg. You write the arrow, that is the anode, is Mg forming Mg2+, and then you write the Soul bridge. Remember, the Soul bridge is there to complete the circuit, and then it's important, is there to maintain electrical neutrality. So the Soul bridge is important, and then you write now Al3+ forming Al. So that is our cell notation, ABC. A for anode, then Soul bridge, then the cathode, and then you are able to get your marks there. Definitely from there, we'll say calculate the EMF of the cell, and then you are definitely going to calculate the EMF of the cell. In fact, calculating the EMF of cell is simply this one, magnesium, you are reversing it backward. Definitely you're just putting a negative sign there. That's what you are doing when you're calculating EMF, because if you put a negative, it becomes positive, and you say 2,36 minus, if you add these two numbers, definitely they will give you the EMF of the cell, but with the reversed one with the negative sign. But we are always emphasizing to say continue to use the formulas that you are given, which is your E cathode, E of a cell equals to E cathode minus E anode. Don't change the formula, please. Copy it the way it appears in the data sheet. Just go and copy it. You can talk about E of the reducing agent, E of the oxidizing agent minus E of the reducing agent is still fine. You can use that formula as well. And you know, reducing agent, you said is magnesium, and the oxidizing agent, you said is aluminum 3+. So you can see that the cathode now is that minus 1,66, which is what E of a cell would be equals to minus 1,66 minus 2,36. And then just using the calculator, you are able to get your answer of 2,36 and 1,66. And then if your calculator is doing well, you'll have 2,36 and 1,66. And then you know it must be 0,7, and your answer must be positive, because we're saying this is spontaneous, which means it's self-sustaining. We don't need external source of energy. It has its own energy, which is enough. So I hope that shows you. And then this is another question that we've given you that you can practice. And then you are having magnesium and copper, and definitely you have seen on the table magnesium there on top of the table there. So definitely on the table you are going to get magnesium 2+ plus 2 electrons given like that, forming magnesium. And then copper, you are having copper 2+ plus 2 electrons forming copper. And then this magnesium was negative 2,36, and copper is positive 0,34. And then you just follow the arrows. The arrows are saying is going upward on the right for reducing agent, is going downwards for oxidizing agent. So you can see the reaction is between magnesium and copper 2+. And then they are forming magnesium 2+ and copper. So you are able to see now the overall cell reaction that you are going to get. You can even be able now to know that the half reactions that are going to take place is magnesium. The magnesium one, you are reversing it. The copper 2+, because it's a strong oxidizing agent, is gaining electrons. So definitely you will have magnesium forming magnesium 2+, losing electrons. You'll have copper 2+ gaining electrons to form copper. And then the overall, as I've shown, the electrons are balanced. So definitely it's your Mg plus copper 2. What is on the left, you write on the left. What is on the right, you write on the right. And you are able to get your 3 marks there. When you say cell notation, you are saying A, B, C. Your anode, you know, is magnesium, forming magnesium 2+. Your salt bridge is double arrows. Your cathode, you are having copper 2+, forming copper. Say, am I right if I indicate the concentration of the ions there of Mg2+? Yes, initial concentration we said is 1 mole per cubic decimeter, so you can show it, it's fine. Am I right if I show the phase is solid and aqueous? You are very right. So you can copy them with the solids and the aqueous with the concentration is right. But even that one will be able to get your 3 marks. And then you can be able to calculate the EMF as well, because you know we're saying E cathode, E of a cell equals to E cathode minus E anode. So definitely you're able to do that. And then your cathode, always the bigger number in terms of this one. The cathode is always bigger, which is your 0,34 minus your anode. In this case, is negative 2,36. And then you just do your signs. I think you will get 34 plus that is 70. You'll get 2,70 volts. So you are able to do that. You can confirm that with the calculator. 0,34 plus 2,36. definitely is 2.7 volts that you get. So if you look at all these questions, they are asking all that which I was doing here, and I've demonstrated to yourself to say this is how you go about answering some of those questions. Look at this question. It says, how will the concentration of Mg2 plus, it's a plus there, how will the concentration of Mg2 plus ions be affected when the cell is functioning? So you are able to see that now as the cell is functioning, magnesium is losing, because magnesium here is alone, is 0. It's forming magnesium 2 plus here when it's magnesium nitrate like that. So magnesium is forming magnesium 2 plus because we said it's a stronger reducing agent, it's a reactant. So it's forming that. Definitely the concentration of magnesium 2 plus will increase because it's busy losing that. But when you go to the cathode side, you will find that we have copper 2 plus that is gaining electrons. So definitely the concentration in the cathode of the metal ions decreases. So this concentration will decrease, this one will increase. But in this case, the question was about concentration of magnesium 2 plus, which definitely will increase. It will increase while the concentration of copper 2 plus will decrease. And then they asked a question there that says the cell is connected to a light bulb. In theory, the bulb should light up, but in practice, it does not. What can be the possible reason for this observation? Remember, the light bulb has what? Resistance. And you will find that the current that is being supplied is low. So when you have low current and the resistance, high resistance and low current, definitely the light bulb won't light. So you are able to explain that and be able to do that question. Now, if we look at electrolytic cell, remember now, I want to emphasize this one with electrolytic cell to say, remember we're doing four types of cells here. You are doing now refining or purification of copper. As an example, it can be purification of any metal. You are doing electroplating, that is number 1, is purification or refining, which is what we have here of metals. Number 2, we are saying we can have electroplating. Number 3, we're having now decomposition of copper chloride solution. And number 4, we're having electrolysis of concentrated sodium chloride solution. So those are the 4 processes. And without any wasting of time, the understanding here is that during purification, it is the metal that loses the electrons to form the metal ions. And then in this loss of electrons is at the anode. In the cathode, always we are writing the reverse reaction, which is the same reaction but in reversed order. So I hope you get that one. And then we are saying in terms of the same happens in electroplating. The object, the metal that we are having, will lose electrons. And then on the cathode, the metal ions will gain electrons like that. And then that's what is happening during purification and electroplating. Hence we are saying the concentration of the electrolyte remains constant, remain the same. Why? Because the rate of oxidation is equals to the rate of reduction. So that's what we are having in terms of this particular cell. And then write down here, they said define the term electrolyte. Remember in these processes we are having salt, which is our compounds that are now when you put a salt in water, it will definitely form iron. So here we're talking about the substance that dissolves in water to give a solution that conducts electricity. You write it as is in the exam guideline. Or the substance that when dissolved in water, it contains ions. It contains the ions. That is your electrolyte. So, and then write down the formula of the cations in the electrolyte of the above. When the write down the formula of the cations. Remember, we're having copper. Is purification of copper. It means we have copper and another copper. And definitely the cations is the positive ions, which is the copper 2+. So that is 9.2. When an electric current passes through the electrolyte, the mass of the electrodes changes. That's the mass of electrode X. So you're able to see X. Remember, we are saying positive, the bigger one. Positive is anode. Positive is anode. The bigger one is anode. Negative, the small one, is cathode. Don't panic. So positive is the anode. That's where X is. And we're saying NOx. Where anode is, there will be oxidation, which is loss of electrons. So the expectation here is that here we're going to have loss of electrons. Definitely, does the mass of electrode X increase or decrease? Definitely it will decrease, because X definitely is going to lose electrons, and then which is copper, because our X is copper, that is copper will lose electrons. So when it loses electrons, it will definitely decrease in mass. It will decrease in mass because there is loss. At the anode, we are losing electrons, then there's decrease in mass. Remember, on the cathode side, the copper 2+ will be gaining electrons, which is the reverse of this. On the cathode side, the copper 2+ will gain electrons to form copper. Then we're expecting this one to increase in mass. We're expecting this one to decrease in mass. So X is the anode, it will decrease in mass. Write down the relevant equation to support your answer. I've already written copper forms copper 2+ plus 2 electrons. So you are able to see that now. These type of questions, you can see they are there to stay, where you have to deal with calculations. Now they are saying the diagram below shows an electrochemical cell used in the refining of copper. Now, during the process, it is illustrated by the above cell, a total of 2,259 times 10 to the power of 24 electrons. You see, it's important to always know those formulas in your data sheet to say, okay, when I'm given mass, I will definitely use this formula to calculate number of moles. When I'm given number of particles, the particles can be electrons, protons, ions. When I'm given number of particles, I will use N equals to N over NA. Definitely, here we're given number of electrons. You can see we are inviting this equation. Number of moles equals to number of particles, in this case, number of electrons, over Avogadro's number, 6,023 times 10 to the power of 23. So you are able to see that you are going to definitely need this to get the number of moles. But what I want to emphasize is that, remember, you are talking about electrons. So we must have what is called mole ratio between the number of electrons. Copper is going to form 2 electrons. Definitely, the mole ratio between copper and the number of electrons. Definitely, 1 copper produces 2 electrons. So the mole ratio is 1:2. This is very important in your calculation. And then, without wasting time, definitely you're going to say, I'm given the number of electrons. You substitute the number of electrons, and then you substitute the Avogadro's number. And then you are going to get your answer, which is 3,7525. And then you are going to use the mole ratio to say, okay, for 1 mole of copper, I have 2 electrons. So I must definitely divide here by 2 to get the number of moles of copper as 1,876. So that is the number of moles of copper. Now I can use the number of moles of copper to calculate the mass. You know, number of moles equals to mass over molar mass. The molar mass of copper is 63.5. When you multiply it by the number of moles, you get the mass of copper, which is 1,19. And if you check, this question is mostly there. In most of our questions, you are getting this type of questions. Sometimes they will ask you to calculate current. So all the time, practice this type of questions, because they are there to stay, and definitely you cannot go to the exam without knowing. And then as we conclude our lesson, I want to emphasize on the stoichiometric calculations to say, always remember this table. It will help you a lot, your data sheet, to always know when we're given the mass, we're going to definitely use that formula. When we're given the number of particles, in this case, we're given number of electrons, we're able to use this to calculate the number of moles. But when you're given concentration to get number of moles, definitely you would use that. and then as well you can use the C equals to M over MV. But now when we are given the standard conditions, STP, standard temperature and pressure, definitely molar volume. Sometimes you'll just be given molar volume. Remember, we had our molar volume at 22,4, the one that we're using at 0 degrees. But for example, when you are at temperature maybe of 25 degrees Celsius, the molar volume will change. It can be 24 cubic decimeters. So always check those conditions. Sometimes you'll be given the molar volume. So when you see molar volume, you know that the formula that you must use is that one. So you will be looking for STP, you will be looking for molar volume on different conditions. Then you will definitely use that. And if you are able to use these equations, we are saying if you know the moles of A, because most of the time you are given information based on reactant A, but you are going to use that information, or on the product, you are going to use what you are given to get what you want. So the only way to move from what you know or what you are given to get what you want is to get the number of moles. After getting the number of moles, you are able now to cross the bridge to use what you have to get what we have using mole ratio. So mole ratio is of paramount importance as long as you are dealing with your stoichiometric calculations and wanted to talk to the issue of percentage purity, to say, remember, we are saying that pure mass divided by impure mass times 100 will give you percentage purity. We gave you example here when we have 5 grams of sodium carbonate, and then we find that the pure one was 4,25. You are able now to calculate the percentage purity as an example, to say, you will say the pure mass divided by total mass, which is the impure mass, times 100, and then you are able to get your percentage. And rates of reactions, we are still emphasizing there to say, remember the definition of reaction rate, which is the change in concentration of reactants or products per unit time. Definitely, you know the reaction. When you see that the reactants are decreasing, you see that this is the graph of the reactants, because when we start the reaction, we're always starting with the reactants. The products are increasing as we proceed. So you are able to see the graph of the reactants and the graph of the product. So you are able to see that and you won't have problem. And then you are able to know that when we're given the heat there, you know it's exothermic. When the heat is added, it is endothermic as well. And then the importance now of the graphs, to say we have here the reaction where we have slow reaction and fast reaction in red there. So you can see the steeper the line or the steeper the curve, the greater the rate of reaction, and faster reactions where the line becomes horizontal finish sooner than slower reactions. But you can see at the end they are ending at the same point, but you can see that there is a factor here. When we increase the factors, definitely the rate of reaction increases, the graph becomes more steeper. So it's important that you have that knowledge. And we are saying, always remember collision theory. And remember the Maxwell-Boltzmann distribution curves. For the temperature, we're drawing for Cape Town, for concentration, pressure, and temperature. Remember, with temperatures, we're saying now what happens, the particles will definitely move, because when we increase temperature, the graph will definitely, it will shift to the right. So it goes down and then shift to the right. So you are able to see that the graph of temperature, it touches there. Be able to draw these graphs and then see that how to use collision theory to explain this. We are always indicating the most important points to say when you increase temperature, you increase the average kinetic energy of the particles. That is the first point that you know. And the second one, we're saying we're going to have more particles. We're going to have a more effective collision per unit time. Please write it in full. You put like that, you won't get any mark. It's more effective collision per unit time. I'm summarizing for you as we conclude the lesson. Now we are saying more particles now, because now you see there's a shift in terms of the graph. You have now more particles that will have energy greater or equals to activation energy. So you increase the number of particles that have energy that is greater or equals to activation energy. And definitely because of that, we're going to have the increase in rate of reaction. So that's how you answer questions like these ones. So for the temperature, we're saying our graph now is going to shift, but it bends downwards, then it shifts to the right, and it touches the original graph, and then you are able to see that we have all that. And then don't know only for increasing the factor, you must as well know about when we decrease the factor, definitely we'll have a decrease in the average kinetic energy of the particles. We'll have less or fewer effective collision per unit time. We'll have less particles with energy greater or equals to activation energy, will decrease the rate of reaction. So know both for increase and decrease when you are dealing with these graphs. And then in terms of concentration, it definitely is on top, because when you increase concentration, you are increasing the number of particles per unit volume. Number of particles, we're talking about it now. Number of particles per unit volume. You're increasing the number of particles per unit volume, just write in English, and then more effective collision per unit time. And then we are saying we'll have more particles that will have energy or kinetic energy greater or equals to activation energy. And then we are saying you will increase the rate of reaction. Please have understanding, write in full, and then be able to collect these marks. And write in bullet form as I'm indicating, so that you can see that for temperature, the other three bullets are remaining the same. I just changed the first bullet there to say for concentration, now it's no longer now going to touch. It will be on top of the other graph. And definitely it means when we increase concentration, we're increasing the number of particles per unit volume. Now, when it comes to the catalyst, now you can see the catalyst, what it does. It provides an alternate pathway. It provides an alternate pathway of lower activation energy. So that's what the catalyst will do. So it lowers the activation, which means it's going to accommodate many particles. Remember, we're having particles here, A, B, C, D, E, F, G, if I'm to represent particles like that. So if you are to lower activation energy, you are accommodating more particles. So it provides alternating pathway of lower activation energy. The other bullets, there will be more effective collision per unit time. Now you'll have more particles that will have energy greater or equals to activation energy. You'll have now increase in the rate of reaction. So even the catalyst does that. The difference is that the catalyst goes inside, the temperature shifts to the right and touches. The concentration is on top of the original graph because we're increasing the number of particles. So you can see it is concentration that increases the number of particles per unit volume. The temperature, the number of particles remain the same. Now, just to look at an example of a question, to say you have 2 H2O2 there, forming 2 water liquids plus oxygen. And they are saying in this experiment A, B, C, you can see the temperature there, 25, same condition, but the reaction experiment A is without catalyst, experiment B is with catalyst. And they are saying in which experiment, A or B, is the reaction rate higher? So you are able to see that, okay, temperature is remaining constant, so it's a controlled variable. But what are we changing? No catalyst with catalyst. So immediately when you add a catalyst, you definitely are going to have a higher reaction, which is experiment B. So you're able to choose B as your experiment. Now use collision theory to explain. So you're going to say a catalyst provide alternate pathway of lower activation energy. Bullet number 1. You're going to say more effective collision per unit time. You're going to say more particles will have energy greater or equals to activation energy, and we're going to increase the rate of reaction. So that's how you will answer, and you will get your answers. And then definitely you will get a question on chemical equilibrium. Just wanted to emphasize here to say, as you revise, look at chemical equilibrium, remember we said it's a dynamic equilibrium where the rate of forward reaction is equal to the rate of reverse reaction. We said there are only 3 factors here that we are looking at that are affecting rates of reactions. It's your capital, so concentration, pressure, and temperature. Remember, rates of reactions, they are affected by about 6 factors there. We said now it's your temperature, it's your pressure, it's your concentration, it's your surface area, it's your nature of reactants, and the catalyst is number 6. So it's 6 factors for rates of reactions, it's 3 factors for chemical equilibrium, and then understand how these factors affect the rate chemical equilibrium. Now, as well, remember Le Chatelain's principle as well. You definitely have to know Le Chatelain's principle, how to state the Chatelain's principle, and be able to look at the graphs of rates and concentration. You will deal definitely with the graphs of equilibrium. Remember, in terms of the factors, you are able now to remind yourself to say, if I look at T1, I can see that what is happening at T1, you can see that N2 here is the one that is rising up. And then you are able to see then that here it shows that there is now increase in concentration of N2. So N2 was added there. We are having equilibrium. When you add N2, equilibrium is disturbed. And remember, if we increase the concentration of a reactant, definitely the forward reaction will be favored. The forward reaction is NH3, so you are expecting NH3 to increase, hence it's increasing. It shows that the forward reaction is favored. And when you increase N2, the other reactant must definitely decrease. So it means now we're expecting H2 to gradually decrease. And then when we have both all our species, our reactants and products, all of them are increasing here. And that is pressure. So when we increase pressure, the concentration of the reactants and products, all of them, their concentration will increase. So don't forget, for the equilibrium graph on concentration, when you increase pressure, you definitely expect that everything must increase. Remember, when you increase concentration of the reactants, only that concentration is increasing. But when all of them increases, you know it's pressure. When all the concentration decreases, you know it's pressure. So when you increase pressure, all the concentrations will increase. When you decrease pressure, all the concentration, which is what is happening at T2, we have increased pressure there. And then if you look at T3, there is no sharp increase in terms of our reactants and products. Then you know it must be temperature, because temperature does not affect the concentration. So the concentration remains at the same place, but now it will only depend on whether the temperature was increased or decreased. You can see that our NH3 there, which is the forward reaction, is this one, is decreasing. So you can see that what is increasing is N2 and H2, which are our reactants, which means we've increased temperature. Remember, if we increase temperature, endothermic reaction will be favored, intermendo. If we decrease temperature, exothermic reaction will be favored. So I hope you have seen, when we increase the concentration of N2 sharply increases, and then the other reactant, which is H2, decreases, and we see the forward reaction being favored. The same you have seen at T2, when we increase pressure, equilibrium is disturbed, but all the species or all the reactants and products, their concentration increases. And then we know that is pressure. At T3, we're saying the concentration remains the same, and it's temperature because it does not change the concentration. However, the reaction, according to the Chatelain's principle, will be able to respond to the disturbance. The last topic as we close is acids and bases. You will definitely deal with all the definitions that are expected under this topic. We have our Arrhenius model. Remember, Arrhenius, he said an acid is a substance it produces. In fact, just go straight to it to say acids produce hydrogen ion. So you're just saying acid produce hydrogen ion in aqueous solution. So in aqueous solution, it produces hydrogen ion. A base produces OH minus. You can just write it like that. A base produce OH minus in aqueous solution. So you just write like that. The issue of conjugate acid and base. Remember, we are saying the difference between a conjugate acid, between the acid and its conjugate base is a hydrogen ion. So they look the same, the difference is hydrogen ion. The one with more hydrogen ion is an acid. The one with less is a conjugate base. The example there being H2SO4 and HSO4 minus. You can see H2SO4 and HSO4, when you look at them, they look alike. The difference is a hydrogen ion. So we're saying the one with more hydrogen is your acid. The one with the lesser hydrogens is your conjugate base. So you must be able to identify the acid and its conjugate base as well, and the base and its conjugate acid. Now, as well, you have done your Lowry-Bronsted model, an acid proton donor, a base proton acceptor. You can't go to the exam without knowing that. You have talked to the issue of strong acids and weak acids, because you got to know that strong acids, we are saying they ionize completely in water to form high concentration of hydronium ion, and then the weak acid, they ionize incompletely. The difference, strong ones is completely and the weak ones is incompletely. And then the strong base dissociates. So we're just using different ways there. It dissociates completely in water, strong base, and the weak base will dissociate completely in water. And don't confuse a strong acid and a concentrated acid and a dilute acid. Remember, an acid is strong or weak, but the strong acid can be dilute or concentrated. So you must be able to differentiate that to say, okay, strong acid, it ionizes completely in water to form high concentration of hydronium ion. But now, when you talk about dilute and concentrated, you are simply saying that we have more number of moles per unit volume. So you have more of a substance per unit volume of water. So you have more number of moles of a substance in proportion to the volume of water. So when you have less water added, that is concentrated. But dilute, it means we have more of the water. So you have less number of moles of a substance in proportion to the volume of water. That is dilute, when you have more water than the substance itself. But when we have more number of moles of a substance in proportion to the volume of water, is concentrated. And we're saying a strong acid can be concentrated, it can be diluted. So concentrated, it depends on how much water it has, and dilute as well. When it has more water, it's diluted. When it has less water or no water added, it's concentrated. And then the last part is the issue of your hydrolysis. Remember, we're saying is the reaction of salt with water, and you must be able now to show whether the salt is acidic or basic salt using the process of hydrolysis. And then you will look at the issue of neutralization reactions, and then be able as well to understand that when you are having a strong acid reacting with a weak base, the solution will be acidic. Remember the issue of the choice of indicators, which in this case will be your methyl orange. And then when you are having a strong acid with a strong base, you will have a neutral solution. And remember, you will be using bromothymol blue. And then when you are having a weak acid and a strong base, your solution will be alkaline or basic. Definitely, you're going to use phenolphthalein. So I always say MBP so that you don't forget. Methyl orange, bromothymol blue, phenolphthalein, and then you are indicating when the solution is acidic, it means strong acid and weak base, and when the solution is neutral, strong and strong. When the solution is basic, strong base, and weak acid, definitely the solution will be basic. You use phenolphthalein. And we always indicate the issue of color changes. Look at that to say when we have acidic solution, we're going to have a red to orange. And when we are having a neutral solution, we're going to have yellow to blue. And then when we are having basic solution, we're going to have colorless to pink. So know those color changes, know the choice of the indicator, which indicator do we use when, and know how to use the neutralization in terms of your governor equation, Ca Va over Cb Vb when you're doing your titration, Na over Nb. Remember, Na and Nb are the number of moles given in the balanced equation. So definitely when you're dealing with titration, neutralization reactions, your titration calculations, you're going to look at that equation. It makes it much easier. And we're saying when you are given these volumes, use them the way they are given. If they are given in cubic centimeter, just use them because you are having volume in the numerator and denominator. They will definitely cancel one another. You don't have to convert your cubic centimeter to your cubic decimeter. Only when you are using the C equals to N over V, you'll have to first do the conversions. But when you're using the governor during your titration calculations, definitely you will use that equation as it appears. And lastly, pH calculations. Remember, we're saying pH equals to minus log H3O plus. Always remember that you have to first find the concentration of the acid. And then if you are given a monoprotic acid like HCl, you know the ratio between H3O and HCl is 1:1. So the concentration of the acid, you just substitute it there. But when you are having a diprotic acid like sulfuric acid, H2SO4, definitely you're going to multiply the concentration of the acid, the H3O plus, you're going to multiply it by 2 because 1 H2SO4 forms 2 H3O plus. So always look at the ratio of the acid to the H3O plus. So if you are given the concentration of H2SO4, definitely you are going to multiply by 2 because it forms 2 H3O plus when you are doing the pH calculation. And if you are given pH, know that you can use the H3O plus is equals to 10 to the power of minus pH to calculate the concentration. And then I will have made a mistake if I leave here without talking about the Kw, the ionization constant of water, which is your H3O plus multiplied by the OH minus, which is equals to 1 times 10 to the power of minus 14. So this one we are saying, please always, when you are given the concentration of the base, you can start here. Come and substitute the concentration of the OH minus in order for you to get H3O plus so that you are able to move back to go and calculate your H3O plus. That is the summary that I came up to ensure that you are ready as you prepare for your exams. I want to say, as I conclude, when the questions seem endless and your notes look like a foreign language, pause and remember, every reaction you write, every mechanism you solve is another piece of the puzzle falling into place. You are not just studying chemistry. You are training your mind to think critically, solve problems, and change the world. Keep going. The molecules may be small, but your purpose is massive.